Hi one and all, this is Steven. Today I am here about Tech Talk presentation. My name is Steven. I am from Aeronautical Engineering branch. My topic is Introduction to Wave Equation. Let's go into the topic. The wave equation is second order linear partial differential equation for the description of waves or standing wave fields. As they occur in classical physics such as mechanical waves, example water waves, sound waves and specific waves, or electromagnetic waves, including light waves also. It arises in fields like uh, acoustics, electromagnetism, and fluid dynamics. A single wave propagating in a predefined direction can also be described with the one wave equation. Look into the look into the string. A pulse traveling through a string with fixed endpoints as modeled by the wave equation. And next, look into the spherical wave coming from a point source in the center. Historically, the problem of a vibrating string, such as that of a musical instrument, was studied by Jean Leron, Alembert, Leonard Euler, Daniel Bernoulli, and Joseph Louis Lagrange. In 1746, D'Alembert discovered the one-dimensional wave equation, and within 10 years, Euler discovered the three-dimensional wave equation. Introduction. The wave equation is the second order partial differential equation describing standing wave field superposition of two waves traveling in opposite directions. This article mostly focuses on the scalar wave equation describing waves in scalars by scalar functions. U is equal to u of x1 comma x2 up to xn into t of a time variable t, a variable representing time, and one or more spatial variables x1 comma x2 up to xn, variables representing a position in a space under discussion. While there are vector wave equations describing waves in vectors such as waves for electrical field, magnetic field, and magnetic vector potential and elastic waves. By comparison with vector wave equations, the scalar wave equation can be seen as a spherical case of the vector wave equations in the Cartesian coordinate system. The scalar wave equation is the equation to be satisfied by each component for each coordinate axis, such as the x component for the x axis of a vector wave without sets of waves in the considered domain. For example, in the Cartesian coordinate system, for E as a representation of a electric vector field wave. The scalar wave equation is dou square u by dou t square is equal to c square into x square u by dou x square 1 plus dou square u by dou x 2 square up to dou square u by dou x square n, where c is a fixed non-negative real coefficient. Using the notations of Newtonian mechanics and vector calculus, the wave equation can be written more compactly as a solution of these two waves. Wave equation can be quite complicated, but it can be analyzed as a linear combinations of simple solutions that are sinusoidal planes wave with various directions of propagation and wavelengths also, but also with the same propagation speed c. This analysis is possible because the wave equation is linear and homogeneous also, so that any multiple of a solution is also a solution, and the sum of any two solutions is again a solution. This property is called the superposition principle in physics. The wave equation alone does not specify a physical solution. A unique solution is usually obtained by setting a problem with further conditions, such as initial conditions which prescribe the amplitude and phase of the wave. Another important class of problem occurs in enclosed spaces specified by boundary conditions, for which the solutions represent standing waves harmonics analogous to the harmonic of musical instruments. The two-wave equation describing a standing wave field is the simplest example of a second order hyperbolic differential equation. It can be also modification place fundamental rules in continuum mechanics, quantum mechanics, plasma physics, general relativity, geophysics, and many others scientific and technical disciplines in case that only the propagation of a single wave in a predefined direction is of interest. A first order partial differential equation, one wave equation can be considered. Wave equation in one space dimension. The wave equation is one space dimension can be written as follows: dou square u by dou t square is equal to c square of dou square u by dou x square. This equation is typically described as having only one space dimension as x because the only other independent variable is the time t. Nevertheless, the dependent variable you may represent a second space dimension. It, for example, the displacement u takes place in y direction, and in the case of a string that is located in the xy plane. And next, derivation of the wave equation. The wave equation is one space dimension can be derived in a variety of different physical settings. Most famously, it can be derived for the case of a string that is vibrating in a two-dimensional plane, with each of its elements being pulled in opposite directions by the forces of another. Another physical setting for derivation is the wave equation is one space dimension utilizes Hooke's law. In the theory of electricity, Hooke's law is an approximation for certain materials starting that the amount by which a material body is deformed is linearly related to the force causing the deformation. It's nothing but the stress. The material body is deformed is nothing but the strain. From Hooke's law, the wave equation is a one-dimensional case can be derived from Hooke's law in the following way. Imagine an array of a little weights of mass m interconnected with massless springs of length h. The springs have a spring constant of k. Look at the picture. And next, here the dependent variables u of x measures the distance from the equilibrium of the mass situated at x, so that u of x essentially measures the magnitude of a disturbance is nothing but strain that is traveling in an elastic material. The forces exerted on the mass m at the location of x plus h are F Newton is equal ma of t equal to m of dou square by dou t square u of x plus h comma t. The equation of motion for the weight at the location x plus t is given by the equating these two forces. Dou square by dou t square u of x plus h comma t is equal constant by mass u of x plus 2h comma t minus u of x plus h comma t minus u of x plus h comma t plus u of x minus t, where the time dependence of u of x has been made explicit. Taking the limit n to infinity h to 0 and assuming smoothness, one gets dou square u of x minus t by dou t square is equal kl square by m into dou square u of x minus t by dou x square. Stress pulse in a bar. In the case of a stress pulse propagating longitudinally through a bar, the bar acts much like an infinite number of springs in series and can be taken as an extension of the equation derived from Hooke's law. A uniform bar of constant cross section made from a linear elastic material has a stiffness k given by the fraction. And next, k is equal to a by l. where A is the cross section area and E is the Young's modulus of the material. The wave equation becomes dou square u of x comma t by dou t square is equal EAL by m into dou square u of x comma t by dou x square, where rho is the density of the material. The wave equation reduces to dou square u of x comma t by dou t square is equal E by rho dou square u of x comma t by dou x square. The speed of a stress wave in a bar is therefore under root E by rho. Algebraic approach. The basic wave equation is the linear differential equation, and so it will be superposition principle. This means that the net displacement caused by two or more waves in the sum of the displacements which would have been caused by each wave individually. In addition, of behavior of wave can be analyzed by breaking up in the wave into components. Example, the Fourier transforms breaks up a wave into sinusoidal components. And next, elastic waves. Elastic waves equation is also known as Navier-Cauchy equation. In three dimensions, describes the propagating of waves in an isotropic homogeneous elastic medium. Most solid material are elastic, so this equation describes such phenomena as seismic waves in the earth and ultrasonic waves. This is used to detect flaws in materials and linear this equation as a more complex form than the equation given above, as it must account for both longitudinal and transverse motion. And wave equation for inhomogeneous media, three-dimensional case. For one-way wave equation, waves are traveling in a predefined wave direction plus c into c or minus c into c. In homogeneous media, wave propagation can also be calculated with a tensorial one-way wave equation resulting from factorization of the vectorial two-wave equations, and an analytical solution can be derived. And lastly, we go into the conclusion. The two-way wave equation is a second order linear partial differential equation for the description of waves or standing wave fields as they occur in classical field physics such as mechanical waves, water waves, sound waves, as seismic waves or electromagnetic waves including light and waves. It arises in fields like acoustics, electromagnetism and fluid dynamics. A single wave propagating in a predefined direction can also be described with the one-way wave equation. Thank you all of you for giving this opportunity, and I'm closing my session. Thank you once again.